Okay, so before we took a break for the test and going over and projects and stuff, we had Work-Energy Theorem, which is just the work done and that's total. The total work done on the object is the increase in its kinetic energy. College Board doesn't like to say KE, they just say K. That's what the pros do anyway. Okay, and that's true as long as we have like the net force in our work for the total work done and change in energy. And we showed how that just comes from Newton's second law. If you're going to have some acceleration, you can just use the equation of motion. That's how this originated in the first place. Um, and you just include mass and simplify to the net force, and then it's all good. That will tell you your change in velocity according to equation 3. Right? So this came using your net force and the total work done. That just comes from equation 3. You multiply by 2 times the mass, and that's it. Okay? On your equation sheet, so I assume you already know how to do net forces and vectors and things like that, so that's really easy. On your equation sheet, it has this really suspicious formula. Delta E equals capital W, that is indeed work, equals integration sign F dot dr. Okay, so take a deep breath. It should be a relief. If F is constant, then this is just F dot, you could say, delta x. It's just its displacement. R, delta R would be 3D displacement. I've never seen them do a three-dimensional problem that actually required much calculation. Delta R is 3D. Right, delta x, delta y, delta z. That's all it is. I've only seen them ask, okay, if you have vectors in 3 dimensions, just take the 3D distance, x squared plus y squared plus z squared, take the square root of all of it. Okay, they never bother. It makes it too complicated and unneedlessly complicated. But what is this dot? That's what we've got to understand today. On the back page, it says A dot B vectors equals AB cosine theta. It also says, horrifyingly, AXB equals AB sine theta. Any idea? Oh, thank goodness. Okay, not horrifyingly. It has absolute value bars around that one. Yes, okay, so they didn't trick you. That's a true formula. If I just did AXB, that shouldn't make a value AB sine theta, that should make a vector. What on earth do they mean? Okay, the good thing for you, the A dot B is really something simple. And it is as simple as, well, if they had vector arrows over A and B, then they would have magnitude. So it's just the magnitude of A times the magnitude of B times mysterious cosine theta. So I'll show you today what cosine theta is, and then if you're careful with it, you can do the whole homework. That's it. That's all there is to energy, is don't mess up this cosine. Make sure you're either using the net force or you're using the appropriate components of the force so that you can work out the total energy or the final change in energy. Any questions so far? Comments? Give me a thumbs up. I already know what this dot product is. The wavy hand, I kind of remember. Thumbs down, this is news to me. I completely forgot that there were 2 kinds of multiplication. Wavy hand, okay. Thumbs down is okay. A few honest people completely forgot. Everyone else, wavy hands. Maybe I remember. Good. Okay. Lucky for you, for energy, we don't need the cross product, the x, so we're not going to bother with this sine theta nonsense. The first thing to know is that when they just write the capital letter, they mean the absolute value, okay? Which is really easy. If they have an ax component or an ay or an az, sometimes 2 out of 3 are 0. Okay, that's just the magnitude of that vector. Sometimes they'll give you the magnitude. Same thing for b. Okay, so they're just multiplying magnitudes. Okay. Now, there's a lot of angles that show up in these equations. Cosine theta of some angle. Okay. What the cross product really means is I want the parallel component. I'm going to take the component of either one, but let's say I start with vector A. I want to take the parallel component of vector B and multiply their magnitudes. And here's what that looks like in vectors, right? The words are really hard to understand. So here I have vector A, and I could always just define it, right? If this is AP Physics, that's supposed to be an arrow. If they give you some weird coordinate system where vector A, my first most important vector, isn't along the x-axis, you can rotate your coordinates so that it is and work out the problem. And if you can keep track, especially on a slow free response problem or some homework where you have plenty of time, you're not racing, okay, you should probably do that. Okay, and remember there's always, and if it looks like maybe you should do that on a multiple choice question, remember those multiple choice, there's always some trick to get it in like less than a minute. Okay, maybe they're trying to trick you into doing that, but this is a long process you should use, like on homework. Okay, so then we have vector B at some other angle. That's what the theta is. Theta is the angle between the vectors, always. So they might give you some other angle, theta, this is the ramp, or this is the incline, or whatever. There's other angles in these problems. If you're doing the dot product, it's always cosine of the angle between the two vectors that you're multiplying. We'll do abbreviate between. The angle between theta. Okay. Well, here's dot product. Excuse me, dot. I get so excited about cross product. It's really fantastic. Let's just make a triangle. So at vector A, I define my axis along my first most important vector. It's really arbitrary, but why not? And then I have some other vector that points at a different angle. Okay, I measure the angle between, or I could do some quick geometry, figure it out. The component of B that points along A is always, because remember we do a physics coordinate system where x, and then we just measure our angle from the x-axis. That's our angle. The component of B that's along A is always, so that would be the magnitude of B times the cosine of that angle, because look, it's a right triangle, because we used a proper axis and everything. So it's B cosine theta times the magnitude of A. And that's it. That's what that's what dot product is. Why would you want that? Well, in a work energy graph where you're multiplying your net force or maybe your components of your force, so I have B is maybe a force vector and x is the displacement. Okay? Remember how on a graph of velocity versus time, you find the area, and that's velocity times time equals displacement. Well, now I have force times distance. Oh, and that's that term that comes out of equation 3. If I have net force times displacement, that's my work. That's my change in kinetic energy. So, so yes, that's exactly why I would want that. And also, that area on the graph is going to be actually some weird rectangle. If you like to graph in multiple dimensions. But it really does have exactly the value of the work. So let's see. I would really have like magnitude of B right here. Oh, you gotta tell me. Does that really add anything to the discussion that that's a rectangle? And you've got some area? Or does it have to be a rectangle? In this case, my delta x would be A. Let's cover that over in black. Yeah, I think it does. Okay. Because I don't know. If I graphed, yeah, it does. I don't know if I should draw a new graph. But this force, we're doing yeah. Oh no. Let's see. Whoops. This is a little bit different discussion, actually. Yeah. Take that away for a minute. Okay. This up here tells me why we would do the cross product. It's the angle between. I want to know how much of force vector B actually moves parallel component, to vector A. So we would get our net force times our real displacement in the energy formula. If I want to reinforce that you can do that real quick. Because if I actually had, yes, it's like I got enough sleep on the weekend or something. Oh, I don't need arrows because okay, so what we do is we realize the parallel components only matter. And I can have some force that actually varies with x. Okay? And this might be mysterious at first, but that same dot product formula also tells me I could just take A times B, and that area would give me the work. So they might also graph. It really is the same idea. I didn't explain it very well. But because you can just multiply parallel components, that gives the dimension of an area. If they decided to graph the displacement or the distance of f, and f is a function of x, obviously it's making this weird trapezoid shape, changing with the distance, you would just have to find the area of this graph between the line and the axis, and that could also give you the work done. Okay? Because that's what dot product really is. It's this weird area between the A vector and the parallel component of B, and it can be shown on a graph like this. It's it's a boring rectangle like on the right if A and B are constants. Blah. Okay, but College Board hates that. They want to be trickier. They'll make the force actually change with the distance. But that's okay. You found the areas of graphs before. As you go through your calculus class this year, you'll do a lot of areas between the graph and the axis. If you haven't done that already, that's okay. It's going to be simple geometrical shapes in AP Physics. Almost always. Okay. Any questions? All right. Well, I think you should try whatever problems you like from those two sets. The earliest thing is due Wednesday. Oh, we'll explain.